All right, welcome back. We are looking at acid-base equilibria still, just doing a lot of examples and kind of showing all the different kind of ways that it's really all the same stuff, but you have to be able to step back and take a look and really think, what am I dealing with here? And so in the case of a weak acid or a weak base, the last couple ones I did were on weak acid, so I thought it'd be important to throw a weak base calculation in here, but really no different. All of these things are kind of interchangeable. So, or at least the concepts on how to solve them, weak acids and weak base. So here's the idea. What is the pH? So what I want to know is what is my pH of 0.75 initial concentration of aqueous ammonia going to be? So when I write out the equation, here's my ammonia. It combines with water. It picks up one of the hydrogens, makes the ammonium ion, and creates hydroxide ions. So if I look up the Kb in my table, in the back of my book, I'm going to find it's 1.8 times 10 to the negative fifth. And so just that's something that you can usually look up in the back of your book, or it'll be given in the equation. And so then what do I do with that? Well, just like my other ones when I was trying to figure out the pH from initial concentration, you need to know the concentration of the ion, either the hydroxide or hydronium ion, that is existing at equilibrium. So you have to take the initial concentration and you have to convert that into the concentration at equilibrium. So the Kb is good because that's the base ionization constant. We've got that. And if we ran an ice table just like we did before, you'd find out that we have we use Y instead of X just to differentiate between base and acid. So the Kb is Y squared, Y times Y, and that's going to be divided by the initial concentration of this. Now, essentially, this should be the initial concentration minus Y, but the same thing applies. If the Kb times 100 is not greater than your initial concentration, then it's so small that it's not going to make a difference. You can just leave it out and shortcut that way. So it's not. You can't, 1.8 times 10 to the negative fifth times 100 is definitely not greater than this, so we're good. But do keep that in mind so you can run yourself a check. All right, so let's go ahead and solve for Y. So when we solve for Y, we're going to multiply by 0.75 here because that's the initial concentration. So we inserted that initial concentration. We want to look at what is Y. What is my concentration of each of these? Once I find the concentration of this, I can get closer to finding my pH. So then I multiply by that, take the square root of it, and I find that my Y equals 3.7 times 10 to the negative third molarity. Now that's my concentration of hydroxide ions. So I could figure out my pOH from that by taking the negative log of my hydroxide ion concentration. So my pOH equals 2.43. But the question asked for pH, right? And we learned that pH equals 14 minus pOH because the pH is it's a 14 scale, so so basically the pH plus the pOH equals 14. So we could morph that around to say pH equals 14 minus pOH. So I just simply subtract my pOH from 14, and that's going to give me my pH. So my pH is 11.57. Let's look at one more quick example in this. What if I was to say that I had a 0.1 molar acetic acid concentration? And so then the idea with that is that this is also a pH of 2.87. So what's going on here? Well, I mean, clearly just a simple, situation of turning this. We could take this, figure out the concentration of hydrogen ions. But the question is, what is the Kb for potassium acetate? Well, this is acetic acetate. I got all this information for acetic acetate. How in the world would I know anything for potassium acetate, much less a base ionization constant? This is an acid. Well, what you have to do is you have to write out these equations and you have to think it through. So if you look at acetic acid, here's what happens. Acetic acid combines with water, produces the acetate ion and hydronium ion. So that's why it's an acid. But this is going to flow back. And we know that this is an acid, and this is its conjugate base. And so there's a Kb for its conjugate base, and there's a Ka for the acid. And we know that any acid and its conjugate base multiplied by each other equals the ionization constant for water, which is 1.0 times 10 to the negative 14th. So here's the situation. But what about this? What about potassium acetate? Well, potassium acetate, when you put that in water, it creates the same acetate ion as acetic acid does. And it leaves behind a neutral cation. See, potassium's group 1 is neutral. It doesn't affect anything, right? And so what we can know by that, since this has no effect at all on this, then this is going to ionize back and create a basic solution, right? Because this right here turns into this acetate ion, and once this acetate ion is in there, it has the ability to flow backwards. And so I rewrote that. So if we're just thinking about the acetate ion flowing back this way, here's what it would do. It would combine with water and turn back into acetic acid. So here's the base, and here's its conjugate acid. Notice it's the same one as this, except reversed. And so we can find the Kb of this, and it's going to be the Kb of the potassium acetate because potassium is neutral, and so it ends up leaving the same ion in solution, which will flow back and cause the same effect as it would have from this one. All right, so I went ahead and worked out a lot of this stuff for you. And so what do? Well, I need to find the Ka because I know that if I can find the Ka, I can figure out the Kb of any conjugate base because Kw equals Kb times Ka. And so I take the Ka, and to figure that out, well, the hydrogen ion concentration is going to be a function of this. So I can take the pH, I can take the antilog of the negative pH to get any hydrogen ion concentration. So here's my hydrogen ion concentration. So once I know that, I can plug that into my formula for Ka. Right? So Ka equals these two times each other, which is going to be, they're each going to have that same concentration. So the hydrogen ion concentration is going to be X, and as well as the acetate ion concentration is going to be X, so that's squared, divided by the initial concentration minus X. Now, this really doesn't make a big deal, but you know what it is, and it's simple enough to throw it in there, so why not? In the other ones, we didn't know what X was, so we just left it out. But if you do know what it is, there's no reason in the world why you can't include it. So we did. So it's going to be divided by my initial concentration minus X, because at equilibrium, the 0.1 is going to be just lost this amount. And so then you can know the concentration at equilibrium from that. And that's kind of ice table logic. And so my Ka is 1.7 times 10 to the negative fifth if I divide that out. My Kw, the ionization water constant, equals 1.0 times 10 to the negative 14th. Always does. It's just always that little number right there. And my Ka times my Kb always equals that. And I know my Ka, I just figured it out right here from all this information up here. And so then I can divide 1.0 times 10 to the negative 14th by my Ka, which is 1.7 times 10 to the negative fifth, to find my Kb. So there's my Kb, and that's the Kb for the acetate ion, essentially. But since potassium is neutral, it ends up being the same Kb for this salt right here. So kind of a backdoor thing and a little bit of logic, you'd have to remember that this is neutral and remember that you can find the Kb of any conjugate base and find out that this just creates the same ion. But a good thing to do if you're ever given write this is write out the reactions. Do find out how they're related. All right, hope that helps.